back to the next lecture, that is lecture 3 on mathematical modeling. We have already had a look at conservation laws, mathematical preliminaries, and one governing equation, that which continuity equation. In this lecture we would focus on momentum equation, and we would derive it from first principles starting from the Newton's second law of motion. Now, let us have a recap of what we covered in the previous lecture. We defined the concept of material derivative and strain rate tensor. Then we obtained integral form of continuity equation using Reynolds transport theorem. Then we used Gauss divergence theorem to derive differential form of continuity equation and its various simplified forms. We also used a simple differential Cartesian differential element to derive the differential form of continuity equation. We would use a similar approach in the derivation of the momentum equation starting from Newton's second law of motion. So, that is what is the crux or the main topic of our third lecture, that is momentum equation based on Newton's second law of motion. The outline of the lecture, we will first start with the origin of forces in a fluid medium. What are different types of forces which we would encounter, how do we obtain their mathematical expressions, and whatever concepts and notations which are involved in description of forces, that is what we would have a brief look at. Specifically, we would see how surface forces and the stress tensor are related, and then we would obtain integral form momentum equation for an arbitrary domain starting from Newton's second law of motion, and in the end we would obtain differential form of momentum equation from the integral form by invoking Gauss divergence theorem, which gives us what we call Cauchy equation of motion. We would also try and derive the Cauchy equation using a differential control volume, and then we will have a look at few simplified forms, specifically the Euler's equation of motion for inviscid fluid. Now, let us have a look at the different forces which we will have in a fluid medium. A fluid medium might be acted upon by what we call body forces, which are essentially non-contact forces which act at a distance. The next category could be surface forces, which are primarily imposed by the contacting surfaces, and we might also come across what we call line forces, which result at the lines of contact with the fluid with certain interfaces, a different medium which might be a solid or a fluid. Let us have a look at a bit more detail about each of these. Body forces first, these arise from what we call action at a distance without any physical contact. There is no physical contact between the agency which causes the body force and the fluid medium. Then surface forces, they are exerted on an area element of the fluid by surroundings through direct contact. Now, the surroundings could be a part of it and the fluid medium, the same fluid medium, or a solid surface. And the line forces, they are primarily involved when we have an interface, for example surface tension. Now, these forces only appear in boundary conditions at the interface of two fluids or at the interface of a solid or a liquid. So, we will not have any further look at line forces in this lecture. We will first concentrate on the remaining to the first two, body forces and surface forces. Now, let us see body forces. These result from the medium being placed in a certain force field, for example gravitational force field, electrostatic, magnetic or electromagnetic force field. In most of the fluid problems, it is gravitational force field is the one which would be involved, and these forces are not confined to specific surfaces or specific areas of the fluid. In fact, they act throughout the mass of the fluid. That is the main or major feature or major characteristic of body forces, and that is why we usually express them as per unit mass or per unit volume basis. Now, let us find out the body force acting on a fluid medium. So, suppose this body force per unit mass is represented by symbol small b. This is a vector quantity. Now, let us take a very small fluid element of volume dV. Now, mass of this differential element dm, this would be the density rho times a differential volume dV. So, the body force on differential material element let us call it dF subscript b. This is equal to b times dm or b times rho dV. To obtain the total body force acting on the fluid medium contained in the volume omega, we simply need to integrate it over the entire volume. So, total body force F of B, this is volume integral over domain omega of B rho dV. So, in this way we would be able to obtain the total body force acting on a fluid body if we know the body force per unit mass. Now, this body force could be due to gravitational force field, electrostatic force field or magnetostatic force field. In many instances it is possible for us to express this body force in terms of the gradient of a scalar quantity. So, in such a situation we call it conservative body force, wherein our body force per unit mass B, this could be expressible in terms of the gradient of a scalar function phi. For instance, in the case of gravity, our phi could be simply the scalar quantity z. So, that completes our description of the body forces, that F b can be given as volume integral of rho b d omega. Next, let us have a look at the surface forces. Now, the surface forces are normally expressed in terms of stress tensor. So, how do we obtain or how do we express the surface force? Let us take a finite control volume and let us consider a small differential area element identified by the vector dA. Due to action of surroundings, there is a force which will act on this small unit area, and let us call or let us denote force per unit area acting on this differential area element as F. So, then surface force on this area element can be expressed as dFs is equal to F times d of A. Now, this surface force can be broken into two components. Normally decomposed into normal and tangential components. For a general case, instead of using these only two components, normal component f of n and tangential component f of t, what we instead do is we use stress tensor to represent the state of surface forces acting on the area element. Now, this stress tensor tau in 3D Cartesian components is given by a 3 by 3 matrix, and we can represent it as tau is equal to tau 1 1, tau 1 2, tau 1 3, tau 2 1, tau 2 2, tau 2 3, tau 3 1, tau 3 2, tau 3 3. So, the stress tensor has got 9 components. Now, if we had a fluid medium in which no torques are present, so in absence of any torques, stress tensor is symmetric, that is, the cross shear components are equal, and this tells us that we have in this case only 6 independent components. Now, of these components, let us say tau I j, this is called a normal component, if I is equal to j, that is all diagonal elements of this stress tensor, they are normal components of stress, and shear stress if I not equal to j. Now, using stress tensor, it is very easy for us to represent the surface force acting on the elemental area. So, in terms of tau, surface force on elemental area dA is given by dF of s. It is a dot product of the stress tensor with the area vector. So, if you want to find out the total surface force on the fluid body, total surface force on fluid body F subscript s, all that we need to do is integrate this differential component of force over the entire surface area, that is F s is equal to area integral of tau dot dA. Now, we can combine the two force components which we have discussed so far, the surface forces and the body forces, and we can write that net force acting on the fluid body F of r, this is equal to F s, the surface forces plus body forces, or in terms of the integral quantities, this is equal to tau dot dA over the surface of the fluid body plus rho b dot dV over the total volume of the fluid body. So, now we have obtained the resultant force, expression for the resultant force acting on a fluid body. Next, now let us move on to the Newton's second law of motion, and Newton's second law was initially stated for a particle of mass dm, and this law said that if we had a particle of mass dm and if it is acted by a force, that resultant force is essentially given by the rate of change of momentum of the particle. So, suppose we have got a particle of mass dm, it is initially moving with the velocity v. And there is a force which is acting on this particle, let us call that force is dF. So, momentum of the particle if you call it small p, this will be given by v into dm. So, from Newton's second law, the rate of change of momentum, that is d by dt of momentum p, is equal to d by dt of v dm. This should be equal to the resultant force acting on this particle. Now, if in case of a continuous media we will not have a particle, in fact we have got a collection of particles which make up our finite fluid body occupying a finite region of space called omega. So, now in this case how do we implement Newton's second law? Newton's second law can be extended in a straightforward fashion by finding out what is the total or net resultant force acting on this particular body. So, net resultant force on the body, which we have already calculated earlier, let us call this as Fr. This could be found out in terms of the surface forces on the body fluid medium and the body forces which act on our fluid body. Now, what would be the total momentum or rather rate of change of the momentum of the entire body? This body could be thought of as if it is composed of many particles having the mass dm, and so we can integrate. If you want to find out the rate of change of momentum of the entire body, we can integrate the momentum of the particle. So, what we have got is d by dt integrated over the entire body. Now, this should be equal to the resultant force which acts on this fluid body. Now, we are dealing with a fixed material region. So, for a region of fixed mass, we can interchange differentiation and integration. So, then what we get is simply this, that we got d by dt of integral small p d omega Now, from here we can identify one extrinsic quantity which we can call momentum of the total body. So, momentum of the total body So, this P would be given by integral over the entire volume dm times V or integral over omega rho V dV. Now, if you look at this expression, we can easily identify that extrinsic property or extrinsic quantity phi, capital Phi, which we use in Reynolds transport theorem. This can be identified with the total momentum of the body, and intrinsic quantity small phi, this could be identified with the velocity field. Now, we would use these two identifications to find out the momentum equation for the fluid medium. To summarize what we have discussed just now, that Newton's second law, we have got dP by dt for the control mass system is equal to Fr, and here capital P is the linear momentum of the fluid body, which can be defined as rho v d omega. Now, there are different possible cases, different ways in which we can choose our control volume depending on our problem. The first case would be Cv is fixed in space, and the second case could be a moving control volume, and third case could be we have got a non-inertial control volume, that is a control volume which is moving with some velocity, accelerating and rotating at the same time. Now, the third case is we are not going to discuss it here. Interested readers might refer to the bachelor's book on fluid dynamics. We will just concentrate on the fixed Cv in space primarily. So, if Cv is fixed in space, we have already seen that P is, that is our linear momentum of the system is defined by this relation P is equal to rho v d omega, and it says that extrinsic property is momentum capital P itself, and corresponding intrinsic quantity is small v. Now, we can use Reynolds transport theorem to obtain what is dP by dt. dP by dt for the control mass system would be the local time derivative, that is del t of rho v d omega integrated over the control volume plus rho v dot dA. So, this is the expression for the time rate of change of momentum for a control mass system which occupies our control volume instantaneously. So, this particular del by del t term, it represents the rate of change of the momentum in the control volume, and this term rho v dot dA, it represents the rate of efflux of linear momentum across the control surfaces. And by Newton's second law, these combination of these two terms should be equal to the resultant force which acts on our fluid body. Now, we have come across a very strange term here in the surface integral rho v dot dA. Now, what is this Vv? We had a brief look at it earlier when we had discussed the tensor products. Now, let us have a recap of what we had discussed and what we mean by this Vv. There is no dot or cross product here between these two vectors. So, what we mean by this simple outer product of velocity vector with itself. So, this particular term which we got in momentum equation, this actually represents a second order tensor which is obtained by outer product of two vectors. So, if you want to compute a particular component of this particular tensor, let us say Vv is ijth component, in fact it is nothing but the ith component of vector v multiplied by the jth component of vector v. So, that is how we obtain the components of this second order tensor, and the product of this second order tensor dot product with the area element, that will give us a vector. That is what we need in this particular equation, which is a vector equation for rate of change of momentum. So, if you look closely, actually the single equation represents the three equations in 3-dimensional space. Now, as we have already seen that the resultant force which acts on the fluid body is sum of surface and body forces. So, we can say Fr is Fs plus Fb, or we can represent in terms of stress tensor that Fs is tau dot dA, surface integral over S, and Fb is the volume integral of rho b d omega. Now let us substitute this expanded form for the resultant force in our previous equation, and then we obtain the integral form momentum equation given by del rho by del t integral over Cv of rho v d omega plus surface integral of rho v dot dA is equal to tau dot dA plus rho b d omega. So this integral form is very useful if you want to obtain a finite volume approximation for solving a flow problem, and it is also very commonly used in integral analysis or overall analysis of complicated fluid system, for instance in the analysis of a turbine system. Now in case of instead of a fixed one, if we had a moving control volume which is moving with a fixed velocity or with a velocity vcv, so we can define a relative velocity Vr is equal to v minus vcv, and we can define relative momentum of the system control volume Pr is rho Vr d omega over Cv, and in this case our extrinsic property would not be P but instead it would be Pr, and extrinsic quantity phi would be Vr, and then we can use RTT. Using RTT we get dPr by dt, that is time derivative of this relative momentum for a control mass system is equal to del by del t of rho Vr d omega integrated over the control volume, which gives us the rate of change of momentum in the control volume plus the surface integral of rho Vr dot dA, which gives us the rate of efflux of the momentum across the control surface. Now this rate of change of the relative momentum Pr for the control mass system, it is related simply by this expression dP by dt of Cm is equal to dPr by dt plus d by dt of rho Vc d omega. So we now got these two equations, we know what is the expression for dP by dt. Using Newton's second law we can replace this by the resultant force, and thereby we can easily obtain an integral equation for momentum for the case where we have chosen a moving control volume. Now suppose we want to derive a differential form, so we would follow the same approach which we have used earlier in obtaining the differential form of continuity equation starting from the integral momentum equation. So now let us have a look at our integral form of momentum equation. So integral form of momentum equation on the left hand side we had the first term was a time derivative del by del t of rho v d omega plus we had a surface integral rho v dot dA. On the right hand side we had the first one was the surface integral in terms of the stress which represents the surface forces tau dot dA plus the last term was a volume integral in terms of the body force per unit mass rho b d omega. Now let us focus on the first case, that is we have got a fixed Cv in space. So fixed Cv in space, then we can interchange the temporal derivative with integration. So del by del t of rho v d omega, this can be written as the volume integral of del of rho v over del t d omega. We would like to transform the two surface integrals which we get here using Gauss divergence theorem. So, let us use Gauss divergence theorem to both of these terms separately. And the application is very simple, rho v v dot dA. So, surface integral of rho v v dot dA is equal to the volume integral of what? Divergence of whatever we get to the left of our dot operator. So, rho v v d omega, and similarly the surface integral of the stress tensor multiplied by the area element, this is tau dot dA, this becomes the volume integral of divergence of tau d omega. So, now we have converted all the terms in our integral momentum equation in terms of volume integrals. So, let us substitute and bring all the terms on one side, all terms on LHS. So, that gives us a big volume integral. The first term becomes del of rho v by del t, plus the second term is divergence of rho v v minus divergence of tau minus rho times b d omega equal to 0. Now, once again we have got an integral which vanishes in our arbitrarily chosen control volume omega. So, we can argue similarly that look, maybe then some parts it is positive, some other parts it is negative, which makes the whole integral equal to 0. Now, then we realize that look, our choice was arbitrary, so we can choose a smaller control volume in the positive part, and once again the same equation must hold good. So, that leads us to the same conclusion that look, the above integral would vanish if and only if its integrand is 0 everywhere, and this implies that del of rho v over del t plus divergence of rho v v minus divergence of tau minus rho times b, this should be equal to 0. Now, we can just redistribute the terms and obtain the differential form of momentum equation. Okay. So, that is what we get in the summary, that application of Gauss divergence theorem leads to a differential form of momentum equation, and we call it as a conservative form. There is a specific reason why we call it a conservative form. Now, this form is del rho v by del t plus divergence of rho v v is equal to divergence of tau plus rho times b. So, on the left hand side we have got the quantities which are linked to the material and the velocity field. On the right hand side we have got the quantities which result from the external effects, that is applied forces. Now, this particular equation is popularly known as Cauchy's equation of motion, and the way we have derived, this was derived from an arbitrary fluid medium. It does not matter whether a fluid is Newtonian, non-Newtonian, compressible, incompressible, it does not matter. This particular equation is applicable for fluid of any type. Now we can also write this equation in expanded forms in a specified coordinate system. Let us have a look at forms in Cartesian tensor notation. So this compact form in tensor notation would be del by del t of rho vi plus del over del xj of rho vi vj is equal to del tau ij over del xj plus rho vi. So this particular equation gives us the momentum equation for ith component of velocity. So please remember, this equation of motion is a vector equation. So it essentially represents a set of 3 equations. Now we said, look, this particular previous form is called conservative form. Why we had called it conservative? Because if you look at each term carefully, the first term is a time derivative del rho v by del t. The second term is a divergence of rho v v. The first term in the RHS is again a divergence of the stress tensor plus rho times b. B would normally be, in the case of gravity, it would be expressible in terms of gradient of some scalar function. So all the terms in this particular equation, they are either a time derivative, divergence, or gradient of a function. So such a form is termed as conservative form of the equation. We can also obtain what is called as non-conservative form of equation. That is very easy. We can use the chain rule of differentiation to expand the first term, this del rho v by del t, expand in terms of 2 terms, and similarly expand the second term also divergence of rho v v, and then apply our continuity equation, and we should be able to get a non-conservative form of momentum equation. Now let us have a look at how do we obtain this non-conservative form. So let us start with the conservative form of equation, and first term del rho vi over del t, this can be straightway broken into 2 parts, del rho over del t times vi plus rho times del vi over del t. So we want to obtain the non-conservative form. Now let us have a look at the second term, del over del xj of rho vi vj. So we can couple the 2 terms together. So this could be written as vi times del over del xj of rho vj plus rho vj times del over del xj of vi. So thus the sum of these 2 terms, del of rho vi over del t plus del over del xj rho vi vj, this can be expressed as, let us first take vi common. So we get del rho over del t by looking at the first terms of the expansion, del rho by del t plus del over del xj of rho vj. So that is, we have gathered the first 2 terms on the RHS of expansions plus rho times del of vi over del t plus vj times del of vi over del xj. Now let us have a look at the first term on RHS. What does continuity equation say? Continuity equation in Cartesian tensor notation was given by del rho by del t plus del over del xj of rho vj is equal to 0. So, hence the first term in the RHS this vanishes, and what we get, that del of rho V I over del T plus del over del x j rho V I V j, this is equal to rho times del V I over del T plus V j del V I over del x j. We can also write it in tensor notation, so dyadic form. So, dyadic form, the left hand side we had del of rho V over del T plus divergence of rho V V, this is same as rho times del V by del T plus V dot del V. Now, this right hand side bracketed term, that can be identified as the material derivative of velocity field. So, we can also write this as rho dV by dt. We do not have to do anything with right hand side, that remains as such in the conservative form or non-conservative form. So, that is the summary. How do we obtain the non-conservative form of momentum equation? Rho del V by del T plus V dot del V is equal to divergence of tau plus rho B. Now, this conservative form is useful in some of the numerical schemes, though most of the time, specifically in finite volume formulations of CFD, we prefer conservative form of momentum equation. Now, let us have a careful look at the right hand side of momentum equation. Left hand side we had density rho and 3 velocity components, but what we have on the right hand side? We have got stress tensor, body force field, that is known to us. So, it is this B is absolutely no problem, B is known to us, but as far as stress tensor tau is concerned, it has got at least 6 unknown components or 9 unknown components if we do not account for the symmetry. So, we see that there are 9 additional unknowns, which that is the components of stress tensor, and they must be somehow related to the velocity field, and for that we need what we call constitutive models, which are required for relating the stress tensor to the velocity components. Rather, we would relate the stress tensor to the rate of strain tensor. Okay. And this aspect we would look at in next lecture when we derive Navier-Stokes equation, and that equation is obtained by using a simplest model, which is a linear relationship between the stress and strain rate, which is applicable to what we call Newtonian or Stokesian fluids. Why these two terms are used, that we will have a look at when we come to the next lecture.